In the last two segments, we looked at two different clustering methods and compared them to each other. In this segment, I want to look at an example. Not a real example, but at least a realistic example. I produced this example as a simulation. I simulated 1,000 cardiac patients with 4 features each. I chose these features because they were related to future cardiac outcomes. The patient's heart rate in beats per minute, the number of past heart attacks the patient has had, whether or not the patient has ST segment elevation. That's an indicator of the electrical system of the heart not behaving well, and the patient's age. Because of course, once you reach a certain age, it does not augur well for your long-term health. Based on these 4 features, I then created a binary outcome for each patient. About 31% of those outcomes were positive. And I should warn you that in medical parlance, a positive outcome is typically not a good thing. I should also point out that this was a probabilistic choice, and so indeed 2 patients with the same features might get different outcomes. Again, very realistic, since there are always latent variables when dealing with human health. Here's a short sampling of some of the patients that we produced. So this patient, for example, had a heart rate of 103, 1 previous heart attack, ST elevation, was 99 years old. Not shockingly, the outcome was not good for that patient. Here's another patient with a good outcome, a heart rate of 80, no previous heart attacks, no ST elevation, relatively young. Not surprisingly, this person did well. The total fraction of positive outcomes in this population was about 31%. Now let's cluster these patients using k-means with k equal to 3. We're going to run k-means 100 times and choose the best clustering, and then evaluate the clusterings by looking at something called the odds ratio. Well, what is the odds ratio? For each cluster, we take the actual percent of positive events, and then we divide it by the expected percent. In this case, 0.312. And that gives us an indication of whether or not we have found a cluster of people who are more or less likely than average to experience an event. Well, when we look at our 3 clusters, it's a bit discouraging. Here are the odds ratios, and they're all close to 1. An odds ratio of 1 says our clustering is no better than random. Well, what's going on? What's wrong here? What's wrong is we worked with raw features. And in fact, that's not always the right thing to do. Let's look at the features we have and observe that they have very different means and variances. So heart rate has a mean of 70 and a variance of 15. And in contrast, the number of previous heart attacks has a mean of 1/4 and a standard deviation of only 1. Age, once again, fairly high mean, a fairly high standard deviation. And ST segment elevation, since it's binary, is kind of the most constrained of all. What this means is that when we use Euclidean distance to measure how far 2 points are from each other, there's an enormous bias towards age and heart rate. Is this a good thing? Well, to quote the immortal Betty Boop, no, 1,000 times no. What do we do about it? We rescale the features so that each variable has exactly the same mean and variance. Here's how we do it. The new value of a feature, x prime, will be computed by taking the old value, subtracting from that the mean value of that variable, and then dividing it by the standard deviation of that variable. For those of you who prefer code to equations, here's how we do it. If we run this code, or evaluate this equation, what will the new mean be, and what will the new standard deviation be? Well, the goal, you'll recall, was that they should be the same for every variable. But what is that? Well, if you stare at it a bit and do a little bit of math, you'll discover that the new mean should be 0 and the new standard deviation should be 1. Since, as usual, I don't quite trust math, I wrote some code to make sure this was really working, in which I used random.gauss to generate some points, and then ran the scaling code and saw what I got. I tested it on 10 points with a mean of 25 and a standard deviation of 3. The original values were this. I scaled the values that were that, computed a new mean. Well, it's not quite 0, but something to the -16th is darn close to 0. And the new standard deviation was, in fact, 1. All right, let's go to the proof of the pudding, the real test. You'll recall that the fraction of positives was about 31%, and that when we clustered with unscaled features, our odds ratios were all distressingly close to 1. However, when we cluster with the scaled features, things work much better. We've got this one small cluster of 108 patients where the odds ratio is again close to 1. But then we have two very nice clusters. We have this cluster where the odds ratio is 0.18. So these are patients who are very unlikely to have a positive event. And this even larger cluster where the odds ratio is 1.45, suggesting that these patients are about 1.5 times more likely than the overall population to experience an adverse event. All in all, pretty convincing demonstration that clustering really does find structure in data.